Good afternoon, everyone. Welcome to the design of reinforced concrete structures problem solving session, week 9. It is scheduled from 3 to 4 p.m. So, today's problem solving session, we will be discussing design of short columns under axial compression with biaxial bending. So, in last couple of lectures, you would have gone through this design of short columns under axial compression with biaxial bending. In the lectures given in week 9, week 8, also in week 7, week 8. This has been discussed in detail in the lectures available online on the NAPTEL side. So here I will be giving you a brief overview of how to solve the problems, and later on we will solve a design problem regarding this. So in case of short column under axial compression with biaxial bending, what happens that in addition to the axial load acting on the column section, we have two moments acting along two principal directions, x direction and y direction. So for that we have to consider the effects of both moments if the eccentricities are beyond the minimum eccentricities. I told you in the last lecture how to calculate the minimum eccentricity, for which the code allows us to use the formula for axial loading only. But if the eccentricity along one axis exceeds the minimum eccentricity, then we have to consider the effect of uniaxial bending as well. Now, if the eccentricity along both the axes exceeds the minimum eccentricity, we have to consider the biaxial bending as well. So for this biaxial bending, here in this figure, you can see that a column section is subjected to two biaxial moments, MUX and MUY. For these MUX and MUY, what code says that this MUX and MUY is taken as some resultant moment MU, like this: mu, which is the square root of mux square under root of mux square plus muy square. You can see that I have shown here a double-headed arrow. Double-headed arrow shows moment actually, and single-headed arrow is the actual load acting on it. The direction of this double-headed arrow is such that right hand rule. The thumb, if you curl the finger along that axis, and the direction of the thumb will show you the moment. Same is in the case of this. So here you can see that MUX and MUY are orthogonal, so orthogonal vectors. So their magnitude or the resultant is given by MUX square plus MUY square. Same same can be done for the eccentricity as well. For the eccentricity, you can see that for this to be the biaxial eccentricity, load has to act here, that is Pu. it is having some eccentricity ex with respect to x axis and some eccentricity ey with respect to y axis. So the if we have to write the combined eccentricity, we can write as the square root of ex square plus ey square. So you have to proceed it like that, this. After that, when the column is subjected to bending along two axes, for example, if eccentricity is such that it is acting on column in such a way that it is making the column to bend like this and bend like this as well. You can say that it's a combination of the two modes. For example, if this is the column section like this, the column will bend like this as well from one side. You can see that from one side it will like bend like this, it will bend like this, and on the other side it will bend like also this. It's the effect of the biaxial moment, that's the moment acting on two axes. So we can see that the column is not now bending along any principal direction like this x or y. It is now bending along different direction. I have shown the axis of bending here, axis of bending, due to which possibly if the moments both mux and muy are so high that whole column section up to this point is coming under compression, because you have seen in the flexure as well, if it's more bending it like the column, making the column to bend like this side will be in compression and this will be in tension, compression and tension. Same is the case here. So the possible location of the neutral axis will be like this side will be in tension and this side will be in compression. Okay. Okay, so in circular column we can have also like this thing. Circular column resultant axis of the bending will be like this, and you will have a possible location on the neutral axis like this. So moving forward, so I have shown here a column section which is having four rebars at the four corners. Mu rx is the moment acting along one axis, and mur is along y axis, another axis. Pur is the uniaxial moment, uniaxial load acting on it. If we see that it will create, if the moments are such that it will create compression here, create compression here and tension here. That's why I have shown the possible neutral axis here, like this. Here it is tension side, this is compression side. So we can draw the strain profiles and the stress block diagram like the same way we did in for beams. We did it for beams by drawing the strain profiles as it varies linearly across the depth. ES1, ES2, ES3, ES4 are the strains in the rebars, and these CS4, CS2, CS3, CS4 is the compression taken by the rebars, and CS1 is the tension taken by the rebar. Here you can see that our column was primarily a compression member, but when biaxial moments act on it, now our reinforcement is helping in taking the tension as well. And so if this rebar would not have been present at this section, so eventually this section would have collapsed here. So there would have been intensive cracking and later it would have collapsed because of high tensile stresses there. That's why you can say that in rebars in